Good day, everybody. Today I would like to share with you critical considerations for an efficient copper milling operation with a focus on using technology for mill lining. What are the main mill liner performance indicators? Your grind efficiency and selecting the correct grinding mechanism for your application. The throughput of the mill, this will be directly influenced by your liner design, as we will see today. Wear life, structural integrity. Structural integrity, this is specifically to protect your shell and heads of the mill. Discharge efficiency, ease of installation, that we will also focus on today. And lastly, environmental impact, where we want to minimize the amount of liner material left towards the end of liner life. I would like to introduce the two opposite ends of the spectrum when I talk about technology and mill liners. On the low technology side, we normally see that there's a single requirement from the customer, and that is only to protect the mill shell and the mill heads using the cheapest possible liners. There's normally no specific focus area from the customer side to further improve the liners, and I quote, "I urgently need a set of liners for my mill." On the high or advanced technology side, there's a requirement from the customer to optimize the liner design, choosing the specific grinding mechanism applicable for his specific operation, optimizing the liner life, throughput, discharge efficiency. There's also a requirement to use 3D CAD liner assemblies, and this is to make sure that the liners fit first time around and that there's no modification required on site. Moving over to the discrete element method that we can use to simulate the trajectory inside the mill as a function of the actual particle size distribution. Computational fluid dynamics and smooth particle hydrodynamics. These technologies we can use to simulate the flow of slurry through your mill as well as through your discharge design. 3D scanning, specifically laser scanning of your mill and mill liners. That is to have a very accurate wear profile to determine the end of life accurately. As well, it can also be used to your liner design based on the actual wear profile. Lastly, online condition monitoring that we will not focus on today. So let's start off with a case study, Africa to Alaska. During the 2020 lockdown, a new customer in Alaska approached us to optimize his discharge head of his 6.4 meter diameter SAG mill. And the requirements were very clear. Double the wear life from 26 to 52 weeks and increase the discharge capacity by approximately 30%. This all sounds easy and achievable, but if you take the distance into account, I've just plotted here one of the routes, and this calculates to be 19,000 kilometers. If you fly a great circle over the North Pole, you can reduce this to 15,000 kilometers. But flying a set of liners halfway around the world is not feasible. So it sounds easy, but all of this without a single site visit or a single drawing. Also, we had to send the second set of liners before we could test the first set of liners. How did we work around these challenges? Well, we used technology. First of all, we asked the customer to perform a 3D laser scan for us of the SAG mill. And in this picture here, you can see one of the pictures achieved by the 3D laser scanner. Some of the liners are removed, and that is to get the drilling pattern of the mill shell and on the head. The post-processing was done by Multotec rubber. And this example here, we have measured the filling segment to filling segment distance to within plus minus 2 millimeters. So definitely accurate enough for this type of design. We also had to make sure that we use accurate data and that we eliminate inaccurate scan data. So this specific insert here shows the discharge head and specifically the drilling pattern on the discharge head, where we evaluated individual scans and compared that to the complete data set obtain a very accurate drilling pattern on the discharge head. The end result was a 3D model of the complete SAG mill with the drilling pattern included. We now had the 3D model with an accurate drilling pattern, but how did we solve the solution, doubling the liner life and increasing the discharge capacity by approximately 30%? We incorporated a spiral discharge design as compared to a radial discharge design that was previously installed. And the main advantage of a spiral design is that it will accelerate your slurry inside the pulp chambers towards the central discharger more efficiently and quicker compared to a radial design. Disadvantage, if you look at the spiral lifter bar, it's slightly longer compared to a radial lifter bar, and it will therefore impact on your available open area inside your mill. So there's a fine balance between the aggressiveness of the spiral design and the open area inside the mill. If we take a look at the specific components in the design, we've incorporated the oversized chrome moly steel lifter bar. That is to accommodate the increase in wear life as well as the spiral geometry. We've used our Multotec grate plate design, where we embed Hardox 500 strips into a rubber matrix, specifically to counter the high wear areas. Moving towards the mid liner, here we have incorporated an integrated liner where we've integrated 2 lifter bars and 2 head plates into a single liner. The biggest advantage of these integrated liners are a reduction of installation time, is cost benefit, as well as an improved structural integrity of this type of liner design. Moving towards the inside of the discharge head or the inner portion of the discharge head, we've rounded this off with a set of protection liners. We've incorporated 2 types of pulp lifters, one with a shortened web in this area, and that is specifically to increase the cross-sectional area as the material flows towards your central discharger. How did we calculate, or how did we determine the spiral geometry? We used the discrete element method, and we did a comparative study between the spiral discharge system and a radial discharge system. We've taken the following performance indicators into account: flowback, where we see slurry inside the pulp chamber flowing back through the grate back into the mill. Obviously, we wanted to minimize this. Carryover, where we see slurry flowing to adjacent pulp chambers, not being discharged in that same revolution. And lastly, maximizing the available open volume in the pulp chamber that is directly behind the kidney shape inside the mill. The second step in the analysis process was to achieve a steady state inside the analysis. The way we simulated the discharge flow was to introduce a predetermined amount of material into 12 pulp chambers. You can see there between the spiral design at the top and the radial design at the bottom. And we then constrained the material on the inside of the pulp chambers until it reached a steady state. We then released the material in the 12 o'clock position in both analyses so that the material is free to flow under centrifugal and gravitational loading. Let's look at the analysis results. This slide shows the material inside the pulp chambers in the 6 o'clock position for the spiral design and for the radial design. Important to note that there can be a tendency for the material to block or lock in this corner in the spiral design. So again, there's a trade-off between the aggressiveness of the spiral geometry and blocking the material in this corner of the design, where we don't see that specific problem with the radial design. This slide shows the spiral, not the spiral, it shows the first pulp chamber being filled in the 12 o'clock position for the spiral and for the radial. And it is clear that for the spiral design, the material is already very close to your central discharger. We compare that to the radial design, you can see the material is still on its way to the central discharger. So already a clear advantage. If we look at the pulp chamber, or the last pulp chamber that was filled with material in the 12 o'clock position, we see that for the spiral design, it's almost completely discharged. There's no material on the 11 and 10 o'clock positions, compared to the radial design, where we see material still flowing towards your central discharger. There's also a lot of material in the 11 and 10 o'clock positions, and this material will have a tendency to flow back into the mill or flow to adjacent pulp chambers. This will severely impact on the efficiency of your discharge system. This slide basically summarizes the two simulations. If I play videos of them, first of all, we see the kidney-shaped geometry. We will then remove the kidney-shaped geometry to just focus on the flow of material in your pulp chambers. And if I can stop the analysis in a specific position, just want to emphasize that the last pulp chamber in the spiral design is completely discharged compared to the radial design. So what was the result of using all of these technologies in this project and in this liner design? And I can summarize this by saying the perfect fit. We delivered the set of liners to this customer in Alaska. It was installed inside the mill without any modifications to the liners. In this picture here, the integrated liner is clear, and here we can see the spiral lifter bar being installed. Moving over to 3D scanning as a condition monitoring tool, I'd just like to highlight the basic facts about the Faro S70 scanner that we use inside mills for condition monitoring purposes, as well as for plant scans. It is compact and portable. We can easily carry the scanner on a plane, and we can carry it into most process plants. IP rating of 54, including an extended temperature range. And this is very important for scanning liners inside a mill. -20 to 55 degrees Celsius, including a relatively high IP rating. Extended range of between 600 millimeters to 70 meters. The range will depend on the reflectivity of the material being scanned. For example, a black surface with a 2% reflectivity can only be scanned up to a range of 50 meters. If we look at the absolute accuracy of the scanner, 2 millimeters at 10 meters and 3.5 millimeters at 25 meter range, but your absolute accuracy doesn't paint an accurate picture of how accurate this piece of equipment really is. A better way to define the accuracy is to look at the standard deviation or one standard deviation. If we take the data that was fitted about a best fit plane, and in this specific case, we're talking about the Gaussian best fit plane. Two examples. Number one, at 10 meters and 2% reflectivity, which is black rubber, we see one standard deviation of 1.3 millimeters, and at 10 meters and 90% reflectivity, which is a white surface, one standard deviation is only 0.3 millimeters. So very accurate and suitable for your mill liners as well as your plant conditions. So it ticks all the right boxes as a condition monitoring tool and as a plant scanning tool. What do we do with the data after we've scanned the liners? We post-process the data using Faro C software, and that is to create an accurate mesh of the point cloud. Another important step is to align this whole data set in 3D space, and we're currently using GOM Inspect to align the point cloud in 3D space. Afterwards, the data can be exported as an STL for further post-processing in most CAD packages. The end result is a very accurate liner wear profile of the complete ring. Whether you choose 4 rings or 8 rings, you can get the wear profile on every single lifter bar and shell plate in that ring. You can then also measure the wear between the new liner and the wear profile. We can also use this tool to optimize the liners based on the specific problem areas inside a mill. This example is a primary mill that was scanned. This is then the 3D mesh showing specific problem areas. Localized high wear towards the discharge, extreme high wear on the discharge itself. The solution: we've designed an integrated liner, chromoly castings in the high wear area with a Hardox 500 strip in the grade plate area to counter the wear. As I explained earlier, the biggest advantage of these integrated liners are that they are easy and quick to install. They are structurally better compared to the conventional liner, and there's also a cost benefit because we are more efficient pressing these liners. Guys, then I would like to summarize with a short case study. It's a 6.1 meter diameter shaft mill in the copper industry. A relatively large grinding media of 125 millimeters, great discharge system, and it's being operated at 75% of critical speed. So taking these mill parameters into account, there's always a tendency to over-design the liners. But that can have a severe or a negative impact on your total throughput as you eat into your effective volume. So what did we do to optimize the mill effective volume as a function of liner life? Well, we started off by plotting the motor input power, the mill motor input power, as a function of your liner thickness. We can see here 150 millimeter thick liner will result in just below 5.3 megawatts of motor input power. Reducing that liner thickness from 150 to 100 millimeters will increase your motor input power to above 5.5 megawatt. So a severe impact on the motor input power by just reducing the liner thickness. We must take into account that this will also then impact your liner life. So what did we do and what did we achieve? We optimized the liner design based on actual wear profiles. And this insert here shows the optimized design where we've incorporated Hardox 500 strips in the high wear areas, a significant reduction of up to 20% on the liner thickness in this specific area. And we've also aligned the liner life with the plant maintenance plan. What did we achieve? A 1.4% increase in mill effective volume. And immediately you would say, but this sounds very, very low and very small. And it is a very small number. But because we're not utilizing the total effective mill volume, this resulted in a 1.7% increase in motor input power. And as we all know, motor input power is a very good indication of the amount of work that's taking place inside the mill. So you can expect a 1.7% increase in throughput as well. And then added advantage, a reduction of 15% in the liner cost. So what do we take away from this? I've shown the importance of using technology for mill lining. For example, 3D scanning, 3D CAD liner designs, and DEM simulations. This will result in the perfect fit right from the first installation. There will be a reduction in installation time. We can also get a detailed wear profile, and from the detailed wear profile, improve the liner design as well as predict accurate end of life of the liners. Using the discrete element method, we can get a more detailed trajectory based on the actual PSD inside the mill, and we can use this data to select the specific grinding mechanism applicable for your plant. And then lastly, geometric optimization of the discharge system. We can use the discrete element method to optimize the geometry of your discharge. In the last case study, mill liner geometry, we have shown that we can optimize the thickness of the liners as a function of the motor input power and the effective volume. We can therefore maximize the throughput of the mill. Mill discharge systems. In this presentation, I've shown the advantages of the spiral discharge compared to a radial design, and we believe that this is a critical area of improvement in your mill liner design. So advice from my side is perform small incremental changes to your liner design to optimize the design. And this will definitely improve your bottom line. Thank you.